So in this lecture, we're going to talk about independence and conditional independence, and specifically, we're going to go um, back into Bayes' theorem and try and see how conditional probabilities work with regards to independence and Bayes' theorem. So that's what we'll work on today. So one of the nice things about Bayes' theorem is that it's really a formula for determining conditional probabilities. And in the case of Bayes' theorem, by conditional probability, we mean the likelihood of an outcome occurring based on a previous outcome in some similar situation or circumstance, maybe. And Bayes' theorem gives us a way to revise predictions or some application based on new evidence. And so it really allows us to do this because in Bayes' theorem, baked into it, is some concept. I'll put this as yellow. It's some concept of like what's happened in the past, the prior probabilities. And I'll put this here as well. Oops. Okay, so it's this idea of a prior probability is really important because in Bayes' theorem, we can use a prior probability, which is the probability of B in this case, and it's our initial belief or like a best guess that event B occurs without any new information that we have. It's just what do we think? So, for example, like the probability that the sun is going to rise tomorrow, or really that the world is going to spin around the sun again, or this Earth's going to spin on its axis and the sun will be there again. The probability of that event happening is very high, and we would say it's very high because our prior probability, right, like the best guess we have is extremely high because for all observable history, that has happened every day. The sun has has risen. So we have a very high prior belief in that probability. So that's a really important concept. And another important concept in Bayes' theorem is the posterior probability. So I'll put that as blue. And that is the posterior probability. And this would be new info. And with the posterior probability, it's the probability that now we're updating after some event B, the updated probability of event B occurring after we learn what has happened with A, because it's the probability of B given A. And we were updating this probability now based on what has happened. So this is a really important concept with Bayes' theorem, is that we update our probabilities based on some prior belief that we have, and then once we get new information, we further update it. And what Bayes' theorem really allows us to do is it provides us a formal way to maybe not improve is the best word, but to update our new beliefs, or as I say, our probabilities, whenever we receive new information. So this is like a big reason why Bayes' theorem is used in it was the quintessential example of like a spam filter, because when you have a classification model that when you get a new piece of mail, it tries to predict whether that mail is spam or not. If you take that mail and mark it as spam, you are updating your prior belief now for the next time that there's a similar mail message. So in these cases, Bayes' theorem is used quite heavily. And another important concept maybe from this slide to think about is this likelihood ratio, and that's right here of the probability of A given B over the probability of A. So what this ratio is a measure of is essentially how much more likely A is to occur if B is true, compared to the overall probability of A, right? So the probability of A given B over the probability of A. So if the probability of A is greater than, let's say, 1, then the probability of B increases after observing some A event happening. If it's less than 1, then it decreases. And so this is Bayes' theorem kind of bakes in these ideas of old information and this ratio, likelihood ratio, to measure how much more likely A is to occur if B is true. And this is a really handy theorem that is used all over the place. It's absolutely something essential and worth really learning. So let's see. One of the key facets to Bayes' theorem is the idea of independent events. So independent event would be, if A and B are considered independent, then the probability of their intersection equals a product of their individual probabilities. So that's where we get, for example, let's try this in blue. So it'll be the probability of the intersection equals the probability of the products of each individual event. And this is a really handy thing that we'll see quite a bit of in the coming slides. And so what really happens is these two statements here, that is this one and this one, winds up being equivalent statements. So and why that is, or what that really means, is for both these statements, for example, like any extra knowledge or info about A does not change the probability of B. So that's what we mean kind of when they're independent events. Both of them are like having any information about one doesn't affect the other. Let's maybe try an example to kind of show how these statements' equivalencies are true. So let's suppose that we have the probability of B given A is equal to the probability of B. So then let's show that the probability of A given B is equal to the probability of A, which is basically just restating what we have up here. But let's go ahead and see how we can use Bayes' theorem to show this. Okay, so with Bayes' theorem, we have the probability of B given A is equal to the probability of B, the probability of A given B over the probability of A. And that's equal to the probability of B. And you can show that the probability of B, the probability of A given B, equals probability of B times the probability of A, and these B's will go away. We can do this and that, and we have probability of A given B equals the probability of A. So we've shown how this one, we'll get to there. Okay. So independent events are going to be very important, and there's certain rules to independent events that we'll be able to use in order to help us solve probability problems. And what this really shows is it's a proof that demonstrates this symmetry here of independent events or independence. If A is independent of B, then B is also independent of A, and we can show that by and cover the steps in this proof is in detail, but essentially we're just saying the probability of B given A is equal to the probability of B. So we'll substitute probability of B in here for this, and then once we've done that substitution into Bayes' theorem, we can multiply both sides by the probability of A, and down here, and then that gives us the probability of A on both sides, and then we also can cancel the probability of B since it appears on both sides of the equation, as long as it doesn't, assuming that probability of B doesn't equal 0, which is a safe assumption to make. So that's how we conclude that the probability of B given A is equal to B, which also shows the probability of A given B is equal to the probability of A. So we have this equivalent definition of independent events now, and it's the same one that I wrote right here. The intersection between the probability of A and B is equal to the product of each independent probability events. And this is a kind of nice definition that we can use when solving a lot of probability problems. We're trying to check for or make sure that we have independence. So we have this right here, and then from the last slide we also encountered those two, and it's maybe one other thing that we can add actually here is a general multiplication rule for this intersection. So we have the probability of A intersection with B, which equals the probability of A times the probability of B given A, and this is for any two events, A and B, their intersection, and this multiplication rule actually holds. So this rule here is nice because it holds for independent and non-independent events of A and B, and only when events are independent. So do we have the ability to say that the probability of A's intersection with B equals the product. Probability of A is the probability of B. So these kind of rules here and the multiplication, I guess I should actually label this. This would be the multiplication rule. These are the types of methods that we can use to check for independence, and for us to kind of start to wrestle or grasp with the relationship between event A and B, and eventually you kind of use this information to calculate like joint probabilities, which in this class and in kind of more difficult questions in this class, we might start to ask you to calculate joint probabilities of events occurring that have overlapping probability events within a space. So these are important rules to work with and try out when you're working on problems. And maybe actually would be good to, let's see if we can think of just a really simple example to show how you would use these. Let's see. So whenever we're like trying to play around with probability stuff, it's always good to think about like either coin flips or deck of cards, or something that's people have a lot of familiarity with, and they're also the rules and the data in a sense, as well as the data generating process are very easy. So yeah, let's assume we have we actually I'm kind of running out of room, so let me just write. So we have a 52 deck of cards, 52 cards in a deck, and let's say that A equals A is the event of drawing a heart, and we'll set B equal to let's do a face card, because there's 4 face cards per suit, and there's 4 suits. And by face card, those are the jack, king, etc. So let's see if these two, because we know the individual probabilities of drawing a heart or drawing a face card. So the question is A and B independent? So how do we do this? Well, we'd calculate the probability of A. So we have to get the probability of A and the probability of B, and the probability of, actually no, we don't need the probability of A. We just need, we're going to need the given. So we'll start by calculating the probability of B. That will be, let's see, there's 12 face cards in a deck, 3 for each suit. There's 4 suits. So that's going to be 12 over 52. Let's just say that's about 0.2, 313, so 0.23. And now let's say what's the probability of B given A. So that's the probability of drawing a face card given a heart. So there are 13 hearts and there's 3 face cards. So that's going to be 3 over 13, which is also equivalent to 0.23. And so then we could show that the probability of B given A is equal. I mean, if you did the calculations here, you'd see that they're, because 12 over 52 is 3 over 13. So these should effectively be the same. This is equal to probability of B. So drawing a heart doesn't affect the probability of drawing a face card. So this is just a quick way to demonstrate their independence, and that's using the fact that the probability. So this is through the we'll call this. Yeah, I'll just do it that way. Not use by the probability given A. I was rewriting it in the color. All right. Let's consider this question. Let's talk about mutual exclusivity. So suppose A and B are 2 events with non-zero probabilities, and I'll give you guys a little hint. This is very important for this question, at least to kind of have the correct answer. Is it possible for A and B to be both mutually exclusive and independent? So it's going to be independent and mutually exclusive. And by mutual exclusivity, what we mean is that there are no overlap in the events happening. So they happen at different times, or one after the other, but they don't occur at the same time. Okay, so you can think about this a little bit, and then we'll go and answer it. Okay. All right, so let's begin by writing down some information. So if A and B are independent, by the previous slide, we then know that the probability of A union B is equal to the probability of A times the probability of B. And we also know if A and B are mutually exclusive, then we know that the probability of A with B is equal to 0 because there is an intersection. They don't occur at the same time. So if we have that, then, or if we have both independence and mutual exclusivity, then we would have the probability of A times the probability of B, which would equal 0. Then, of course, that means the probability of A equals 0, or the probability of B equals 0. However, remember, because they're non-zero probabilities. So in this case, the answer would be no. All right, so let's work on a problem and see how a Venn diagram can kind of help us solve this. Because unlike the partition problems that we did before, and if you remember those where we have some space like this, maybe we have like A, B, C, D. All of these are mutually exclusive and sum up to 1. And that's not necessarily true for probabilities like we have here, because obviously we have 2/3, 3/4, 11/12, which equals more than 1. But the thing is that we're getting those calculations that equal more than 1 because these are overlapping events. So there's essentially kind of double counting you can think of. So we'll draw a Venn diagram to kind of help us solve this type of problem, and then go through the admittedly mundane calculations of all the arithmetic that we'll have to do. But we'll just kind of go through that really quickly. Okay, so let's see. Let's draw our, I just also label this too. Let's do black. Okay, let's draw this right here. All right, so in this space, we have 3 events. We'll call them, we have A, B, and C. So we know that A and C are independent, and B and C are independent, and A and B are mutually exclusive, which means that A and B can never happen together. But A and C and B and C can happen together. So let's draw let's actually do this in black. Now we'll do it in green. And then we'll do okay, so we'll call this A, this B, and this C, and then we'll have the probabilities in here. So remember that remember that A and B do not and that's gonna be really important when we do these calculations. So let's do where A and C overlap is, of course, the probability of A and C. And I'll start using some shorthand here, actually. So we'll call and I'll carry this notation through to the actual calculations. So we'll say this is A, B, and C for some shorthand. So the probability of A and C overlapping is AC, and the probability of A happening and not C is just going to be A minus AC, and this will be the same for B as well. And then for C, the probability of C happening is the same exact thing. It's just C minus AC minus BC. So that kind of gets rid of the overlaps. You'll notice here that we don't really care about the space that's not included here. So this would be 1 minus A, B, C would be all of this space here, essentially. But for partitions, all of these do take up the entire space and add up to 1. So that's one of the big differences here. If you're looking at this Venn diagram and saying, why aren't we drawing A like that and B like this? It's because of the independent nature of them. Okay, so, and you don't have to draw Venn diagrams, but they are very helpful sometimes to kind of get a sense for how these things interact. So let's go ahead now and solve these things. I guess we have we're basically creating 3 equations, and we'll have 3 unknowns for each of the probabilities. So this will get a little bit dicey, but let's go ahead and try. So we have our first one, second one, and third one. So this is the probability of, this was A union C, or A or C, B union C, and then B union A union B union C. So we're just taking these things and putting them back over here. So the probability of A union, we'll start with C, equals, and then the probability of B union C, and this is the big one, A union B union C, and this is A plus C minus A times C, and this will be B plus C minus BC, and again, this is the probability of A plus the probability of B. We're using the shorthand here, minus the overlapping spaces, and for this we had 2/3. Write that a little bit nicer. 2/3, 3/4, and 11/12. Okay. Now, one important thing to keep in mind and just to make it so we see these still, these multiplication of probabilities. Why are they here? Where do they come from? Well, remember, this in yellow, that the probability of A, or let's say C, or it could be B and C, but this is just the intersection of them, is equal to the probability of A times the probability of, in this case, of C, and that equals AC, because A and C are independent. That's kind of the big thing here. Are independent. We know that from these. Okay. Let's see. We are going to need to use these values in these calculations. So let's go ahead and go on to the next step, which is going to be plugging them in and solving for them. So we'll start by doing this plus this one. So that's going to be, turn off my phone. Okay, so that's going to be, where were we? Yeah, we'll call this 1 plus 2, and this is going to just be A plus B plus 2C minus AC minus BC, which will equal our 2/3 that we had from above, plus our 3/4. And we'll do something a little bit different for 3. I guess maybe I'll put a box around these. So for 3, we're trying to show A plus B plus C minus AC minus BC, and that gives us 11/12. And then the other thing we're going to need is 1 plus 2 minus our 3. Okay, and for that, that's going to just be, this is how we're going to find out what C is equal to, because we're trying to take the probability of A or C and the probability of B or C and add them, and then we're removing the probability where they all overlap, and that gives us our C, because C is an unknown, and we have C minus AC minus BC, and we have to get the AC and BC, which means we have to deal with the A minus AC and the B minus BC. So this is simply going to be C, which will equal 2/3 plus 3/4, and we get that from here, and minus 11/12, which of course we get from right here. Again, we're just taking this, and we're plugging them in here. So to actually solve that, we're just going to do some arithmetic. So this will be, we can get the 2/3 and 3/4 to behave with the 11/12. So this will be 8/12 plus 9/12 minus 11/12, which will equal 6/12, which will give us 1/2, which will be equal to C. So we'll put a little box around that for now. Okay, let's go on to, now that we have C, we can plug C back into 1 and back into 2. So now we can do 1, and this is going to be need C for 1, and then we can also solve 2 now. So for 1, this is going to be just A plus 1/2 minus 1/2 times A, which is going to equal 2/3. Again, that 1/2 is, just to make it clear, we're taking the 1/2 we got for C and we're plugging it into this guy right here. So this is this plus the C. Okay, so that's going to give us 1/2 A, which equals 2/3 minus 1/2, which will equal 1/6. And then we have A equals, this is just straight arithmetic and algebra, which equals 1/3, I believe, which will be our A. So we'll go ahead and do that. And then for the second one, it's the same thing. We're going to put the C back in. So this will be, we have our B plus C, which is 1/2, minus B times C, so minus 1/2 times B. It's going to equal 3/4. So this is the original equation we had, and maybe not also, just to make it a little bit more clear. I hope this doesn't become too messy, but I think it's maybe a little bit important to kind of see what's going on. And then we can maybe say we need C here, which is getting plugged into all of these things. Okay, hopefully that's a little bit clears things up a little bit because there's a lot of numbers on here. Okay, so this gives us 1/2 b, and this is going to be equal to the 3/4 minus 1/2, which equals 1/4, and then this is going to give us b equals 2 times a fourth, which is going to equal 1/2, which is our final answer for b. Okay, so that's the three final answers for A, B, and C. So the probability of A is equal to 1/3, and then for B and C, those are just both 1/2. That's our final answer. Okay, so it's kind of a long one, but it kind of shows a few things. One thing of I think noting is the importance of understanding what's going on between these overlaps and interactions, and how we're using the overlaps to kind of take to remove them to get back to the original probability of A, because the intersection or the overlap has the extra information into it. So maybe like to think a little bit more about this Venn diagram. A minus AC is just the probability of A minus the intersection of A and C. And this is just the intersection of A and C. And it's kind of like a big thing. And this is just C minus intersections of AC and BC. So yeah, I think that's good for this problem. Let's go on to the next one, which will be cards. And so here we have a deck of cards, 4 suits, 2 colors, and 2 through ace in each suit. So suppose you draw 2 cards one at a time, and A is the event that the first card is a heart, and B is the event that the second card is a club. So we have, we care a lot about hearts, and B is the event that the second card is a club. A club. And hearts, diamonds, clubs, spades. So we want to know is if you draw the cards with replacement, are A and B independent? And the answer to that is pretty simple. That's going to be yes. And we can kind of show that, right? You can say that the probability of B given A is equal to 13 over 52. And we know there's 13 cards in each suit. So we also know that the probability of getting B is also equal to 13 over 52. That means these are independent because the probability of either event happening is the same. So what if you draw the cards without replacement? Are A and B independent now? So this one in yellow. So without replacement. The answer here is no. And why not? Well, if you think about this as our probability space, right? This is S. Then if we take, one card out, then S is equal to S minus the one card now. And so we can no longer pick that card. So the probabilities are changing. It's more likely to get other cards now. So once you remove, let's say, one heart from the deck, the remaining cards are less likely to be hearts because there's less hearts than, there's hearts minus 1 versus spades, clubs, and diamonds. So the probability of that would look like probability of B given A is equal to 13 over 51, which would not be equal to 13 over 52 now, which is the probability of B, and that's if without replacement. So the key idea there is to look at the 51 and the 52. Okay, let's get this a little bit more complicated now. Let's say we have two events, so we have the same deck of cards, and A is the event that the card is a heart, and B is the event that the card is a face card. So let's draw some, let's draw some stuff. Let's say A is yellow, and A is this, and we'll use purple, which is B, and that's getting a face card, so it's J, Queen, and King. So that's going to be those right there. So this is B, and this is A. Okay, so the question is, are A and B independent? So let's try and solve this. We have here the probability of A, which is equal to 13 over 52, because we have 13 cards in each suit. And that is 1/4, because we have 4 suits. This is 1 suit. And the probability of B is equal to 12 over 52, or if we simplify that, 3 over 13. And the probability of A intersection with B is equal to 3 over 52, which is the probability of A times the probability of B. So yes, these are independent. Another way to kind of look at independence is, or another way to interpret it would be the proportion of face cards within A. So we could actually write that over here maybe. So the proportion of face cards within A would be the probability of B given A, which is 3/13, and that equals the proportion of face cards within the entire deck. So, which would be the probability of B, which is equal to 12 over 52, and we already did that as 3 over 13, and so same, but I'll put a little note here. This first one is the proportion of face cards in A, and this is going to be the proportion of face cards in the whole deck, and we'll call the whole deck S for the sample space. And we can also use a little bit of highlighting and say the proportion of face cards within A is equal to this, right? Those are the face cards in A. So face cards in A. And if we want to draw a Venn diagram of this, so to speak, or wanted to visualize it, we could draw a box. Kind of, those are our deck of cards. And what cards do I use? Yellow and purple. So yellow would be A, and we already know that it's there, and then B, and the area that we care about is in there. So before going any further, we're taking this probability space we draw and we're kind of generalizing it to this picture here. So and then of course this is S, the whole deck, as our sample space, and we want to show that the probability of B given A is equal to the probability of B, because this is If so, they're independent events. And the way to look at, we'll do it here. So this is the proportion of A taken by B, and then this one is the proportion of S taken by B. And so these independent events are equally likely from happening. So oops. Okay, so we're talking about, cards, drawing cards, and esoteric letters with probabilities. How do we kind of bring this back to the real world? And when can we really assume independence? So assuming independence is a tricky thing because we don't always have independent events in the real world. In fact, we almost never do. But assuming independence really simplifies calculations by a lot, and it makes real world scenarios much more manageable mathematically, and we can apply basic rules of probability if we assume independence. And oftentimes that gives us a good approximation of an answer, which is close enough. The reason why we can't we know things aren't independent is because we often have a lack of information. We often don't have all the data, or we're trying to capture a very complex interaction with a small amount of features. And all these things kind of give us reason to assume independence and to approximate these probabilities. So that's just kind of like a, honestly, probably it's mostly because it makes, not to lie, it makes the math manageable and easier. Okay, so let's do another quick example before we start to talk about conditional independence. So, right, that's next. Yes, conditional independence. Okay, so in this example, 1% of UCSC students are data science majors, and 25% of UCSC students eat extremely expensive avocado toast for breakfast. Assuming that being a data science major and eating these expensive avocado toast for breakfast are independent, we want to know what percentage of data science majors eat avocado toast for breakfast, and what percentage of UCSD students are data science majors who eat avocado toast for breakfast. And the important thing here is this would be a very difficult answer or question to answer because there's a lot of information we don't know. Let's say, maybe, in a hypothetical world, that DSC welcomes all new students with a all-you-can-eat free avocado toast breakfast. And that primes these students, specifically data science students, to want to eat avocado toast in the future because Avi the avocado was a data science student, and he opened an avocado farm and made a deal with HTSI to sell them bulk avocados cheaply. So there's a lot of background deals going on, and students are now being primed, specifically data science students are being primed to want to have avocado toast for breakfast. And wouldn't you know, Avi the avocado farmer opened up an avocado stand right on campus at the farmer's market. So now data science students actually do eat more avocado toast on average than other students. But do you see how complex and convoluted the story is? And there's a lot of assumptions in there that we would need to make in order to capture that, right? That probability that data science students are a little bit more likely. And so instead of thinking of all that complexity or going out there and finding it, and who knows if we ever could find it, we just assume independent events. And if you can think about how much more difficult the math would have been to take into account all those things I just said that went into the event of data science students eating avocado toast. This becomes a really easy problem because what percentage of DSC majors eat avocado toast for breakfast? Well, that's just the probability of avocado toast given a DSC student, which is equal to the probability of avocado toast. And I guess actually I was put avocado, so I did that before, which is just 25%. That's it. And what percentage of UCSC students are data science majors who eat avocado toast for breakfast? Well, that's just the probability of avocado toast intersection with DSC students. And that equals the probability of avocado toast times, and this is the same rules we've been using all along, probability of being a DSC student, which is 0.25 times 0.01. And we get these, we get these numbers just from up here. And this just gives us 0.025, which equals 0.25%. And we didn't have to assume a bunch of stuff. We just made these very simple calculations, and sure, if that story was true, then these percentages would certainly be off. They probably wouldn't be off very much though, because we're still dealing with larger numbers here, and these information that we previously got is probably not too far off. And so even if this percentage was, let's say, in the case where we did have Avi the avocado farmer colluding with HDSI to sell students lots of avocado toast over the next 4 years of their college careers, this percentage wouldn't be terribly far off. Now, maybe that is completely wrong. Maybe there's some other event that happened which made it so that, you know, HDSI is forcing students to eat avocado toast for breakfast so they can't, you know, take their final exam or something. Then, yeah, these ideas here, the set of the problem winds up being wrong and incorrect. But by and large, making assumptions and, you know, to assume independence based on some data that you have is not a terrible idea. And it provides a very good baseline too, that we can use to think about the problem space. All right, so sometimes we have events that can become independent once you learn new information, or sometimes they can become dependent given additional information. So, for example, we might have like a deck of cards, and we might know, for example, a card that we've pulled, and we might ask ourselves, does that change the probability of another card being pulled? And these conditions are often based upon what it is that the original probability that we're seeking to try and find out. So the main things here to keep in mind are the fact that we're being given additional information and new information. So conditional independence is based upon what we're being updated with and how does that change our probability space. So let's do a couple examples. So in this case, we have our deck of cards again. And so the deck of cards is our sample space. And let's say that the A is the event that a card is a heart. So we'll go ahead and draw that. So that's going to be all these possibilities. That's A. And then we have B, which is the event that the card is a face card. And so that would be kind of like the same box we had before. However, this time, our dog ate the king of clubs. So we can just go ahead and kind of consider this as being gone now. So now gone, right? So we had our dog, grabbed it, ran off. So now the king of clubs is gone. So we have to ask the question now, are A and B independent? And we can do some calculations and find out. So we have the probability of B given A, and that's going to be the probability that the card we're drawing is a face card, given that the card is a heart. And so that's going to be 3 of 13. So we also can then look at the probability of B, the event that the card is just a face card. And we have 11 out of 51. So 11 out of 51 does not equal 3 out of 13. So we would say that, no, these are not independent events. Another way that we can kind of look at this is take the probability of A, which is 13 out of 51, and that's the probability that the card is a heart. We have all our hearts, so that's a 13 out of 51, and we can take the probability of B, which we have already calculated as being 11 out of 51. And we can ask the question of the probability of A's intersection with B, which is equal to 3 over 51, which is not equal to 13 over 51 times 11 over 51. And that we get that from the previous slides with the multiplication rule, the probability of A, the probability of B, because this would be true if they were independent. And the fact that it's not tells us that this is not independent. Okay. So I guess one last thing we can say here is like from an intuitive point of view, what has happened? Well, the missing king of clubs has affected, well, I suppose maybe a better way to think of that, yeah. Okay, so the thought here is the king of clubs is now missing. So because the king of clubs is now missing, it has slightly decreased the overall proportion of face cards in the deck, right? Because we have one less face card. So we still have 4 jacks, we still have 4 queens, but now we don't have 4, we only have 3 kings. So the number of face cards in the deck has decreased. But that hasn't affected the proportion within the hearts, right? Because we still have these, so the hearts remains unaffected. So this creates a small but significant difference between these independent, what were independent events. So that's why they're no longer independent. You know, the somewhat comical but perhaps real life scenario of a dog eating one of the cards and introduces a subtle dependency into these two events. Okay, now let's look at one where we have new information. So we still have the scenario where the dog ate the card, the king of spades, or the king of clubs. So we're going to use yellow. Okay, it's yellow, and then this was A, and then I think I used blue, and I should write that. That's B. And in this case, I think it's still gone. Okay, so suppose you learn that the card is red. So here we have an example of that you draw one card. So now we're saying that the card that we've drawn is red. So with this new information, we now know that the card we've drawn comes from the red cards. So we no longer need to worry about any of these black cards. So the spades and the clubs, we don't care about anymore. So these are now gone. So we just ignore those. So now we want to ask, you know, are A and B independent given this new updated information? Well, let's try it out. Do purple again. So we'll say the probability of B given A is equal to 3/13. which is 6 over 26, which is equal to the probability of B. So, and this is within the red cards, which is why we're dealing with 26 now. And primarily we're concerned with face cards. That's why we have these 6. So that's where that comes from. And then the fact that we have all these is where that comes from. And another thing that we could write is, maybe for some intuitiveness, so within the red cards, A as an event and B are independent. So what was before independent is now become, or before dependent has now become independent with this new information, because even though the dog still ate this card, when we drew a card, it came from the reds, not the blacks. So it doesn't matter if one of these cards was missing. Heck, all of these can be missing except for that 2. And yeah, it really doesn't matter because we're no longer dealing with the 2 black suits. We're dealing with just the 2 red suits. So essentially the missing king of clubs affects the black cards, but not the red cards. So when you're kind of solving probability problems like this, whenever we get new information, and there'll probably be an exam question where you're calculating some probabilities, and then we'll provide you with some new information and ask you to recalculate things given that new information. So this is a pretty good example to kind of think about, and we'll do more of these in class. But yeah, that's the this problem illustrates how dependencies can persist or not based on, I guess both these problems show how these dependencies between probabilities can exist or change based on the conditions of what's currently going on, whether you're drawing a red card or a black card. And yeah, I mean, it kind of just it shows the subtleness there. All right, so for conditional independence, right, because these independent events are now being conditioned on something happening, like drawing a red card. So recall A and B are independent if this equation or this comparison holds true. So the intersection of A and B is equivalent to the probability of A times B. And when we say that these things are now conditionally independent, we're just saying that this entire probability and this one now get an added condition to it, which is some C. And that C now needs to be true in order for this, right, intersection of A and B, given that C has happened, equals the probability of A, given that C has happened, times the probability of B, given that C has happened. So this kind of idea of where the C comes from, we'll highlight it. So this C comes from the definition of regular independence, which you've seen before. But we've added the C to everything because we're now conditionally talking about the independence. So it's just an extension of that. And this condition has to hold true across all of these probabilities. It just like, it wouldn't make any sense to just have, this where you have the probability of the intersection of A and B given C is equivalent or equal to the probability of A given C times just the probability of B. B would still need to have that condition because we're looking at the intersection between A and B. So you have to have the conditional event on both of them. And another way that we could actually check for this would be, let's say, the probability of A intersection with B intersection with C over the probability of C is equal to the probability of A's intersection with C over the probability of C times the probability of B's intersection with C over the probability of C. So this is another form of the equation that you can use to check for independence. So going back to kind of real world ideas, why is this conditional independence important? Why is there this pragmatic approach to conditional independence similar to the same one that we had before with just assuming independence? And there is a lot of the same ideas here. It makes calculations easier. We're working in a limited data space, but ultimately, one of the big key takeaways is that the complex systems that we live in are ever evolving. Think about COVID-19. There is constantly new information coming out, and with that new information, we're trying to update things, and a lot of the updates are now based on this new info we have. So before a independent event might now be dependent, or vice versa. So assuming conditional independence is just fine. It makes things a lot easier for us, and it's a good starting point in our modeling. All right. So like the avocado toast example, here is one where we're looking at a population of UCSD students, and 50% of them, all right, so 50% of UCSD students like Harry Potter, and 80% of UCSD students use Discord. We have Discord and Harry Potter. What is the probability that a random UCSD student likes Harry Potter and uses Discord, assuming these events are conditionally independent, given that a person is a UCSD student? So this winds up being a pretty easy problem. If we didn't assume conditional independence, then this becomes a rather complex problem. But if we assume conditional independence, then we can say we'll use some shorthand. That's fine. We'll say love Harry Potter intersection with Discord users. Actually, let me do that as black as well. Okay, given that you are a UCSD student is equal to the probability of liking Harry Potter, given that you're a UCSD student, times the probability, and this is just straight from the previous slides, of Discord, given, again, that you're a UCSD student. Now remember, this condition of UCSD is kind of like our C. So UCSD is equal to C. This is like from previous slides. I believe I used a green highlighter for that. So this is like essentially our C. We're talking about this C. These C's right here. So if we use the 50%, 80%, this is just a straight 0.5 times 0.8, which is 0.4. So that, assuming the events are conditionally independent, this is the probability that a person both likes Harry Potter and uses Discord, given that they're a UCSD student. Okay. So let's extend this a little bit. Is it reasonable to assume conditional independence of liking Harry Potter and using Discord, given that a person is a UCSD student? So that's what we want to kind of ask. Is that a reasonable assumption to make? Because if it is, then you saw how easy this was to calculate. Also, is it reasonable to assume independence of these events in general among all people? So when we look at conditional independence and then making these assumptions, we always need to consider the population for which we are making an assumption. So think about these things, specifically think about what this stuff really is saying, what it means, and we'll go back and I'll give you a few seconds to think about this. All right, so first thing to think about is these things. And then we can talk about this one. So is it reasonable to assume conditional independence, of those things given that you're a UCSC student? And I think this is a reasonable assumption that could be made because UCSC students, while diverse and unique, definitely have a lot in common. They tend to be younger. They probably grew up with Harry Potter at some level, so at least with the movies. So it's safe to assume that if a person is a UCSD student, we can lump in the population of UCSD students to generalize this conditional independence. So I'd say that's a yes. Is it reasonable to assume independence of these events in general among all people? And this is probably a no. And one of the big reasons why is because of age. There's a couple big ones, but age is one, and then location. Granted, Harry Potter probably has international appeal or acclaim to some level, and so might Discord, but there probably are other options for, like, for example, WeChat versus Discord, right? Or other types like Line or other messaging apps instead of Discord. So I think age and location might be good things that would cause us to not want to make the assumption of independence among the events in general of all people. So the answer here would be B, conditional independence only. And again, that condition, just to make sure it's clear, that condition is based on person's a UCSD student. So that's what we're kind of tying together here, are those two things. So the final thing we'll look at is this idea of independence versus conditional independence. And we want to show that there's no intrinsic relationship between these two things. And maybe another way to think about it is that you can have, for a sample space, with the right conditions, both independent and conditional independent events and constraints in the system. So we'll look at an example of all four of these. So for the first one, we have the setup will be the same for all of them. The only thing that'll be different are the scenarios. So consider a sample space of S, which I've already drawn out here. So this is S, and all outcomes are equally likely. So we create a partition space of S, and we want to specify events A, B, and C that satisfy the given conditions, and we want to have events that are not impossible to create. So we're going to keep within these bounds for the events in our probability space. So let's go ahead and create, we'll do A in yellow. So we'll say A is equal to 1, 2, 3, and 4, because the deck of cards example was kind of easy to draw out and see. So we'll kind of follow that same pattern. B is going to be 3 and 3 is below 7, 3 and 7. And we'll say C in a different color. We'll use blue. We'll use blue for the highlighter as well, yeah. So C will be equal to 2, 3, the middle 4, 6, and 7. So as always, let's kind of draw out our sample space and the probabilities for these that we're dealing with. Let me just rewrite this. So we know that's S. Okay, so we have A is yellow, so that's going to be that right here. That's A. And we have B is green, that's 3 and 7. And then we have, with the blue, we'll highlight 2, 3, 6, and 7. So that's going to be 2, 3, 6, and 7. And this will be, this will be C. Okay. So in this first scenario, A and B are independent and are conditionally independent given C. So let's go ahead and write that out. So we have A and B are independent, and for that we know that we can test this by looking at A's intersection with B, and that should be equal to the probability of A times the probability of B. And we know the probability of A intersection with B is the number 3, so it's just 1/8. Right, that would be this, and that's going to be equal to 1/2 the probability of A, because A covers 4 numbers, times 1/4 the probability of B covering 2 numbers. That checks out. And then the other thing is A and B being conditionally independent given C. So let's see what that looks like. We know that's the probability of the intersection of A and B, C, and that's going to be equal to the probability of A given C times the probability of B given C. So probability of A given B is, if A intersection with B is 1/4, because again, it's not, it has this condition here, conditional, so we're dealing with this kind of space. And then particularly where A and B intersect. So A and B only intersect here, which would have normally been 1/8, but now we're conditioned on C. C happened. This would be kind of like us drawing a red card. We only care about the red cards now, not the black cards. So we only care about these 4 squares, not these outer 4 ones. So out of these 4, the intersection of A and B is only 3, thus 1/4. Okay. So that's going to equal the probability of A given C is 1/2, and the probability of B given C is 1/2 as well. And these things look good. So this scenario is good to go. We've shown that A and B are independent and are conditionally independent given C. And to make this a little bit more apparent given C, and that's where these C's come from. All right, let's try another one. So in this one, we still have the same as before. So our A is still going to be these 4. And what do we use? We use green for B. Still going to be these 2. And now, given C, we will highlight, maybe we'll do, let's look at the scenario, right? A and B are independent, but are not conditionally independent given C. And knowing that we have to keep in with this, let's set C as being equal to we'll go these 2 and these, and we'll also add this time the 5. Let's see what happens. So we're saying this is black. Again, A and B are independent, and then we're also checking for A and B not conditionally independent given C, which is just this part here. Okay. So again, A and B independent. Let's go back and look at A's intersection with B, which we know is 1/8 from before, and that equals the probability of A, which is 1/2, times the probability of B, which again is 1/2. In this case, it would be 1/4. Okay, so 1/2, 1/4, we're good. Now, the tricky one is down here, A, B not conditionally independent given C. So let's do the same thing as before, probability of A's intersection with B, C. Since it's not conditionally independent, this time it's not going to be equal to, or let's see, yeah, we should be able to show this. A given C, if not, we'll pick a different space for C. B given C. Okay, so probability of A given C is going to be 2/5. And, right, because C is 5 and we have two things in A that overlap with C. And the same thing for the probability of B, 2/5. That is not going to be equal to the intersection of A and B given C, which is 1/5. Now, where do the 5s come from? The 5s come from the fact that C is 5 large. And then this 1, 2, and 2 here is just the space that A overlaps with these 5, and that B overlaps with these 5, and that A and B's intersection overlaps with these 5. So that's where it comes from. So good. Okay, so this shows this scenario of A and B being independent but not conditionally independent given C. All right, on to the next one. Let's change A little bit now. We'll still stick with yellow, and let's see. A and B are not independent but are conditionally independent given C. So A and P are not independent but are conditionally independent given C. So we know that the probability of A intersection with B, since they're not independent, that can't be equal to the probability of A times the probability of B. However, they are conditionally independent given C, so we would need to show that the probability of A's intersection with B given C is equal to the probability of A's given C times the probability of B given C. So let's see what we did here. A and B, so this should actually be given C. And this one we did these 4. Oh, it's actually given C as well. Oh boy. Okay. All right, let's try setting A equal to just 3 this time. So 1 through 3. That's A. And we'll pick B as being these two. And this time we will say that the conditional space will be the first 3. And we'll also include these 3. All right, let's see how that works. So the easy one is so the easy one is A and B not being equal to independent. So that would be the probability of A's intersection with B should not be equal to the probability of A times the probability of B, and the probability of A is 3/8, because A covers 1, 2, and 3, and the probability of B is 1/4, or really 2/8, but we'll call 1/4. And the probability of A's intersection with B is just the 2, so that's 1/8. So that's not equal. Okay, so that condition holds. So A and B are not independent. So now let's check for the conditional independence. Let's A, B are conditionally independent given C. So here we have the probability of A's intersection with B given C is equal to the probability of A given C times the probability of B given C. So probability of A given C is 1/2 because A covers 3 squares and C covers 6. B would be 1/3 or 2/6. So we'll say 1/3. And this is the probability of A and B's overlap given C, and A and B overlap on just 1 square, and that's 2. So that's 1/6. So that's all looking good. All right, let's try the last scenario. In this case, A and B are not independent and are not conditionally independent given C. So that means the probability of A and B's intersection can't be equal to both individual probabilities being multiplied. And that also means that the conditioned version of those can't be true as well. So let's set A to being, let's use the same, let's try this out. Let's use the same 3. So that's A. And for B, we'll use our original 2. All right. So this one did not satisfy, are not independent. And neither did, this one didn't satisfy conditional dependence. And this satisfied both. So it's 4, 5, 6. 6, 7. Okay, let's try doing these 6 again, but let's add a 7th one under C. Let's add 8. So that's C. C there just in case. Okay, so not independent, and then we'll say A, B, not conditionally independent. Actually, this is B given C technically. Okay, so probability is the same thing. A is with B is not equal to the probability of A times the probability of B, and the probability of A in this case would be 3/8, and of B that would be 2 for 1, simplify 1/4. That does not equal, they overlap with just 1, again that's 3 1/8. Okay, this given probability of A's intersection with B given C is not going to be equal to, because it's not conditional. Probability of A conditioned on C times the probability of B conditioned on C. So A conditioned on C is 3/7, and this is B on C, 2/7 again. These 7s come from the space of C. And then this one would not be equal to the intersection of A and B, which is 1, given C, and C is 7, 1/7. So this holds true as well. Great. So we showed that given the same sample space, we can find events and arrange them such that all 4 of these different combinations are true, right? All four of these are true. We've shown that with these simple examples. All right, so this lecture is long enough, so just a quick summary slide you can look over. What we really covered and we really looked at were independence between 2 events and how knowing about one event, does not need to change the probability of the other event. And then we looked at this idea of conditional independence and how applying a third event, C, can give us new knowledge about what's going on in the probability space and potentially change that probability, increase or decrease it. And we also showed, finally, with those 4 examples, there's no relationship between independence and conditional independence. They're mutually exclusive. They can happen together. So we're going to switch from this kind of, in the next lecture, going from this basic probability examples. These are sort of the linear algebra versions of the probability lectures, I'll say. But it sets us up nicely to understand naive Bayes and how to use Bayes' theorem to build a classifier algorithm for prediction. Because those are all going to be based off of probabilities and updating probabilities and assuming independence. So this is where it's all kind of going towards. So yeah, we will go ahead and we'll end it there.